Let's move on. I move here. I say field in design optimization. Engineers encounter fields when optimizing design. The goal is to create objects that will not fail in service and still be economical to manufacture. It is a fake product. A fake product is synonymous with inadequate. When you say a product is fake, you are talking of inadequate engineering and production skills. So there's not enough engineering in it. It is your burden to design, prototype, and manufacture real products for Nigeria and Africa. This set of courses are in place to stimulate your minds and provide you with skills and trade tools to do these things. We are trying to stimulate your mind with skills and trade tools to do this. So even though this course is a course in mathematics, you are learning graphics, and you are learning symbolics, you are learning programming, you are using all of these things to be able to bear on your mark. That is how it has to be for an engineering student. You cannot separate these things. I can't teach you graphics, I can't teach you math without bringing graphics into it. Because without the graphics, you cannot see the math. And so many other things that work together with it. Remember that we express our gradient in terms of the directional derivative. We say the directional derivative of a scalar function of the vector x is in direction of u is u dot the grad of f of x. If you forgot this formula, go back to old notes. We spent a lot of time explaining this. With a scalar value function, this is scalar value function with vector arguments that are now position vectors in the Euclidean point space. So even though the points in the Euclidean point space are the locations are points, but once you join a point to the origin, you got a vector. So whenever you can join a point to the origin, it's no longer a point, it's now a vector, and it's a position vector. A position vector is a vector in every way. The reason why we still continue calling it position vector is to remind ourselves, how it came about, how it was born. You know, there are some things. We define the gradient in this limit is a directional derivative. So this is the directional derivative, and it is the limit as alpha tends to 0 of phi of x plus alpha u minus phi of x over alpha. And then we were able to prove last term, or not last term, before the strike, we were able to prove that it is this quantity here dot u, and this quantity in bracket is called the gradient of phi x. So the gradient of phi x. So if you want to get it, just take the dot product of the gradient with the unit vector in that direction. That's the relationship between grad and the directional derivative. And you can write it in the autonomous system. ONB here means autonomous basis. That is, an example of autonomous basis is your Cartesian coordinates IJK. Another example is your spherical coordinates or your cylindrical coordinates. There are many coordinates that are autonomous base coordinates. So that is those are the autonomous bases. This is the grad. So components of gradient, what we are introducing another way to represent derivative. So for instance, you know that if we say d phi x dx I e I, you remember from our summation convention that there are how many components it is. I will go to the chat room to see whether you remember. How many components do we have in this d phi x the x I e I? I want you to go to the chat room and answer me. How many components do we have there? I'm waiting for you in the chat room. How many components do we have? Okay, somebody said 3, 6, 9. Those of you who said 3 are correct. The people who said 9 are wrong, because if this is a scalar, and because the repetition, repetition shows summation, so you have to add 3 things here. So remember that. So remember that, and if you have used it to eat EBA, just begin to think about it again. And so what we are saying here is that we can call that grad of phi x, or we can say is d phi the xi ei. And we are introducing a very powerful notation, which is the comma notation. So if I say phi comma I mean you are differentiating phi in the ith component, that is xi. So you take this equation as a defining equation of this quantity phi comma I. That's a new thing. And that will make life very easy for us. Very, very easy. So instead of writing the phi, the xi, we just say phi comma I. That means that you are differentiating phi with respect to the first coordinate. So if I say phi comma 1, that is the phi, the x. Phi comma 2 will be the phi, the y. Phi comma 3 will be the phi, the z. So that is, so I'm using this equation to define something for you, which we shall use. And things get a little bit interesting as we are moving on. Addition, product, and other rules apply to gradient in the common notation as follows. For instance, if you say phi psi comma I, is you are differentiating a product. So if you are differentiating a product, you differentiate one, and then you differentiate the other. So all the rules that you know, if you now want to write it out, because phi comma I, EI is grad of phi, and psi comma I, EI is grad of psi. So just understand this. You have been introduced to a new notation called the comma notation. If we agree with that, we can now move on and say that gradient of anything, grad of anything, and we are generalizing now. We will generalize this to vectors, to tensors, to everything, to scalars, to anything we do. Grad of anything, we are representing the gradient operator as a postfix operator. And the gradient of anything is simply that thing, comma, alpha, circle times E alpha. There is a label with a generator around here. You see, this will give us some little long quiet. Okay, so phi comma alpha. So this is the definition of. So if this thing is a scalar, then this circle times becomes a simple multiplication. But if this is a vector, then you are going to get a dyad. We have discussed dyads before. Then if it is a tensor, you are going to get a triad and so on. But this is a very powerful notation that will make some results so easy to explain. We will not go to the proofs of these results in this course, not because we cannot, but because it is not our primary goal for this course. We will do that in another course. Where as long as the coordinate system is autonomous basis, the comma signifies partial derivative with respect to the alpha coordinate. So if alpha is 1, it is the partial derivative with respect to the first coordinate. If alpha is 2, it is the derivative with the second coordinate. If alpha is 3, it is the derivative with the third coordinate. Usually you have 1, 2, 3 coordinates for. Those are the kind of things that are of interest to us right now. Now I said if it is, as long as the coordinate system is autonomous basis. What happens if the coordinate system is no longer autonomous? The truth of the matter is that this formula is still correct. The only thing now is that comma is no longer a partial derivative. It is now something far more complex. It is called a covariant derivative. I will not take you through covariant derivatives in this course, but I will give you the benefits of covariant derivatives without learning covariant derivatives. You can ask mathematical, you can put something in Cartesian coordinates, you can write it easily as partial derivatives. And you can now ask mathematical to give you the same thing in spherical coordinates or in any coordinates of your choice. In fact, I think you can even define a new coordinate system and mathematically calculate it. It will calculate all the covariant derivatives for you without you needing to know anything about it. Those are the benefits of modern technology that we do not have to learn all the theories behind anything before we can begin to reap the products of using them to solve problems. So this is a much better way to express things than this way, because this applies now even when we are no longer dealing with autonomous basis. I made the mistake of saying spherical and symmetrical autonomous. They are autonomous, but they are not linear. So autonomous bases are bases that are not the bases where these partial derivatives are bases such as Cartesian. When it is not Cartesian, then this thing is no longer just a partial derivative. It is now a more difficult derivative, which we will not get to, but whose results we will use as we need. Because that means that if you have this now, by the time by next 2 lectures, you'll be able to see. Okay, suppose instead of Cartesian coordinates, suppose this is cylindrical coordinates. How do you express grad? And then you will get the results given to you. Once you can get the result in Cartesian, you can use Mathematica to ask for the result in spherical or any other coordinate system you want. So that is how we are going to do it. I will not take you through the computation of those things, but I will take you through how to apply and obtain the results that are in those areas. Take this now as the definition of grad, because that thing can be anything. Can be a scalar, it is correct. Can be a vector, it is correct. Can be a tensor or higher order element. This formula is correct as long as you understand that whenever we are in Cartesian coordinates, the comma represents just partial derivative. When we are in different coordinate system, the equation is still correct, but the comma is now representing covariant derivative, which I will spare you of for that. But you will get the results from Mathematica will spoil you by giving you the result, and you are going to be able to do much more complicated things than you can even do ordinarily using this much more advanced computational formula for the grad. Okay. What happens when you have the gradient of a vector function? You can see now, if we look at what we had before, gradient of something is that something comma alpha times alpha. Now, because that something is Vxei, because it's V1 E1, V2 E2, V3 E3, where V1 is the first component of the vector in the first unit vector, V2 E2, the second component in the second unit vector, and V3 E3. Comma alpha applies only to the coefficient. It does not apply to the vector basis, because in Cartesian coordinate, the vector basis does not vary. Therefore, we can go from here to here. So you now have Vi, comma alpha, because it's only the component that is differentiated. And then you now see this dyad here, Ei, E alpha. So again, I want to ask you a question now. Please go to the chat room and tell me, how many components are we looking at here? How many components? I want you to go to the chat room and tell me, how many components will this thing have? Okay, so smart guys. So everybody can see immediately. Because consequent from the double summation, if you write out all the 9 components, you will see, I am giving you to you like this. You can write all the 9 components. Let I rotate from 1 to 3 and alpha rotate from 1 to 3. You will have 9. You could also get them in this matrix form. You can have this matrix, this 1 by 3, 3 by 3, circle times 3 by 1. It will give you a single thing with 9 components of this, 9 components with each one with a dyad as a coefficient of a dyad. You can try that out. You can write it out here or write it out here. But I always prefer we just get used to the comma notation, because the comma notation makes life exceedingly easy for us to apply to much harder stuff later on as we move on. Okay, so thanks for participating lively in that. So that you can remember that. Good. So suppose we have a tensor field. The tensor field itself has a dyad already. So if you have Tij, Eig, the tensor field has 9 components already. When you say comma alpha, as usual, the vector basis, whether they are single or dyads or triads or tetrads, they are not affected by the comma. So the comma is only affecting the coefficient, and therefore this is what you have. And you can see that this, when you have a second order tensor and you take its gradient, we are going to get a third order tensor containing 27 terms. Each set of 9 terms can be written out as we have done for the tensor gradient and so on. So you can continue going using the command notation allows us. And you can see now why there's a problem when you are no longer in Cartesian. For instance, the reason why it is so easy to get the result of this comma is that the comma affects only the coefficient. But if you go to spherical coordinates, the basis vectors, as we have seen before, can be differentiated. You can differentiate E, R, E, theta, and E phi. You can differentiate them. So the problem becomes complicated, and that problem is solved only by introducing a new kind of differentiation called the covariant differentiation. But we will not go into that, but just restrict yourself for analysis purposes to Cartesian. When we need things that are non-Cartesian, I will show you how to get those results using mathematical without doing any stress. Once you just remember how to get anything in Cartesian, you are okay. Because use mathematical, you can get it in any coordinate system you like, even without understanding the fundamental basis of how it is done. For now, why are we not doing that? Because it is not our purpose now. It will distract us, and I don't want to distract us. I want us to go to what we want to achieve in this course. Temperature is a scalar field, but the gradient is a vector field. Velocity is a vector field. The gradient is a second-order tensor. You can see that, but as soon as you remember this formula, you will see that every time you take gradient, it increases the vector order, the tensor order by 1 because of this circle times E alpha that is involved in the gradient definition. So everything goes up 1 step. So if you have a scalar, the gradient, what's temperature? It's a scalar. What is temperature gradient? That's a vector. What is pressure? If you state pressure as a scalar, pressure gradient will be a vector. But pressure is a different beast. It's a much more complicated beast. I don't like to talk about it in this class because to talk about it will require almost a whole lecture. But let us just leave it at that and move on. Okay, so this is the gradient of a tensor. So when you have triad, we started with dyads, then we can have triad, we can have tetrad. All those things are defined just the way the dyad was defined before. So if you have U, V, W, and Y that are vectors, the triad U circle times V times W is defined by the fact that when you operate it on Y, it creates a dyad. So a triad is what you operate on a vector to make a dyad. And a tetrad is what you operate on a vector to get a triad. That's how all those definitions go. But we are not going to go beyond. We are not going to do much more than the dyad. It's only once in a while that some of those results we just intrude on our piece. But it's good for you to know that we are not going to go too deep into them. Now, on page 14, we are now looking at something very interesting, which is called the trace of a tensor. A tensor is a second order that has dyads as the basis rather than vectors. The vectors come in pairs as basis. So just let us look at the tensor, which is the second order. So how do you get the trace? If you want to, because you can always express a tensor as a linear combination of its dyads. Let us go back and take a look at one thing we have done already. I want to just go back and show you something. Okay, for instance, see the grad of V. You can see that because grad of V is a vector, therefore its grad is a second order tensor. But you can see that everything there is in form of a coefficient multiplying this dyad. So once you understand how to deal with this dyad, all that remains is just a scalar, coefficient. That's all. So anything you want to do to a vector, once you have done it to a dyad, you are okay because you can just like I always express vectors as unit vectors, as a combination of unit vectors. You can always express tensors as combination of dyads. You can express third order tensors as combinations of triads. You can express fourth order tensors as combination of tetrads. And you can continue like that ad infinitum. So when I am talking about trace here, and I am saying I want to apply to a tensor, which is a second order tensor, all I am doing, I'm just limiting myself to what happens to a dyad. Once I have already explained to you what happens to a dyad, I don't need to go further because every tensor can be expressed as a combination of dyads. Every tensor can be so expressed. So there's no problem with expressing your tensor as a combination of dyads. So once you know what to, so if you want to take a trace of a tensor, just take each dyad and change the circle times they are to dots. What you have now is a scalar, and that is the trace of the tensor. How do we do it again? You want a trace of a tensor, take every dyad it has and change its circle times, change that to a dot. If you change it to a dot, what you have, so the trace of this is simply u dot v, is a trace of this. Now, I told you before that taking a gradient promotes something by one level. I want you to tell me now, if I have, first of all, I cannot take a trace unless I have second order or higher. You cannot take a trace of a vector. Doesn't exist. That's why you have not had a trace up till now, because you have only known about vectors. But once you go to higher order vectors like tensors like second, third, and higher orders, you can take traces. How do you take a trace? You take a trace by changing the circle times to a dot. I have a question for the class. Now, are you promoting or demoting a tensor when you take its trace? If you are promoting or demoting it by how many orders? One order or two orders or three orders or four orders? Those are the two questions. Promoting or demoting, or, and if you, whichever one you answer, by how many? Remember, if it is a gradient, you are promoting by one order. If you are taking trace, you are you promoting or demoting, and by how much? Okay, good. Okay, it is great. So the class is very smart. So once you take a trace, you are demoting by two orders. So if you have a tensor, you take its trace, you have a scalar. So you are demoting. So it's just like somebody is in a, if I want to take your trace now, which level will you be? I just take you from 300 level, I dump you back in 100 level. That is how to take your trace. So, like some of those students that have offended the university or have caused some serious crime and they rusticate, sometimes they trace them. They take a trace of such students. They take them from 300 level and dump them at 200 level. That is how to take a trace. If it's 400 level, you want to take the trace of the student, you dump him from 400 level, dump him at 200 level. So I hope you see that it is not a nice thing to take your trace. I mean, so but if you want to take a trace of a tensor, you take the dyad operator there, you change it to dot, and when you complete what is left, you see that it has been demoted by two orders. So if you have a third order tensor and you take its trace, what will you get? If you have a third order tensor and you take its trace, what will you get? You have a third order tensor and you take its trace, what will you get? You say you are going to get a vector. Good. You are going to, if it's a third order tensor, you are going to get a vector. If it's a second order tensor, you are going to get a scalar. If it's a fourth order tensor, if it's a third order tensor, you are going to get a second order tensor. So taking the trace is a demotion by two orders. Good. So let us learn another thing here. Now, when the order is more than two, we have to be specific on the trace on how the trace should be taken. Because when we have a second order tensor, there is only one product there. But when you have a third order tensor, there are two. You can take the left trace or the right trace. So you cannot just say, take me the trace of this third order tensor. Then I will ask you, which of the traces do you want? Because I can take the trace on the left, I can also take the trace on the right. Things get even more complicated when you have higher order tensors. But luckily for us, we are not going to be looking for higher order tensors. Most of the time, we will not exceed third order. And even third order, we only go into it occasionally. When we do deal with tensors, most of our work will be at second order. So don't worry about them. You are not going to have any ambiguity resolution needed because taking a trace of a second order tensor is not ambiguous. But taking a trace of a third order tensor is ambiguous. But usually, whoever is telling you to take the trace will make it so clear that we know where the trace should be taken. So usually, when you are going to take the trace, only one trace is important, and you will quickly know which trace it is. Let me give you a hint. It's usually the trace on the right, but just know that. But it will be clear that that is the one that is important, not the one on the left. But you will see why it is so as we move on. So the trace of a tensor is a demotion of that tensor by two orders. Now, the divergence is a trace. What we call divergence is a trace. Gradients of objects larger than scalar are at least second order tensors. That is, gradient of a vector is a second order tensor. Such derived fields can be contracted in the following way by taking the trace of the last two bases. So when you want to take a trace to get a divergence, you are only concerned with the last two bases, that is the traces on the right, when there are more than two. If there are only two bases, there is no ambiguity. Such a contraction, which a contraction is what comes here, is just like, when you burn wood, you get ash. So when you take a trace, you get a contraction, you get something, you get a waste product. So that waste product of the trace, whether you burn your wood, you get ash. When you take the trace of a tensor, you have contracted it. Such a contraction is called a divergence. That is, how do you get a divergence? You have a vector. Let us go back and take a look at an example. See what you have on this page 11. Can you see page 11, everybody? I think can page 11 say?
Yes, sir.
Can you see page 11?
Yes, sir. I can see page 11.
Okay. Look at page 11 here. In page 11, we started with vector V, which is a vector. Then we took its gradient. Grad V is V EI cross E alpha. If you take the trace, I want you to take the trace of this and take the trace of this quantity there, VI alpha, EI circumference, that's E alpha, and simplify. I want to know whether you can see the interesting thing that will come. Remember that when you take the trace, you have demoted it by 2. So if it's a tensor of second order, you are going to get a scalar. Take its trace and show me and tell me on the and tell me as clearly as you can on the chart room. Take the trace of this graph and let us see. Take the trace of this graph. And let me see it. Nobody's answering me yet. I want you to take the trace of this graph, because the graph has now become a tensor. So take the trace and tell me precisely what you get. Don't just tell me it's a scalar. Take the trace. Don't tell me it's diagonal. Write it out. What is EI dot E alpha? So EI dot E alpha, Habib, you are almost doing well, but not quite, because you have forgotten that there is still I comma alpha. That's that V. Habib, that V is differentiated. It's not just V. So Habib is getting close, but I want to see others try. Habib, others, take the trace of this quantity. Let me see. Okay, what I'm going to do, I'm going to give you 10 minutes break. We are going to meet again at 5:40. Or make it, 5:45. Make it 15 minutes break. Make it 15 minutes break. And we will see what we will move from there. So by that time, you will go to the chat room and tell me what you haven't taken a trace of this quantity. At that point, I will give you the answer. So see you again in 15 minutes time.